Okay, so what I would like to do this time is another exercise. So this time what I want to do is exercise 28. So exercise 28, the first part of it at least says that if we have a sequence tending to x, then twice that sequence tends to twice x. So if you've got a number tending to a limit, then you double every term in the sequence, then the result is that it tends to twice the limit, which should seem straightforward. Okay, so how are we going to do this? So it said prove. In the question it said prove using the epsilon n definition. So remember, we've got this at the top. This is a thing that should be emblazoned on our brain here. So you just have to learn that. You have no option, just you've got to learn it in the right order with the right words. Once you've got that, then we can have a go at this. So you have to decide what it is that you know and what it is that you want to prove. So we know that xn is tending to x. So the definition is this thing, so we know that this is true. So so we know that whenever we have a number bigger than 0, there is some number n, so that the difference between the little nth term in the sequence and the limit is less than this number, this positive number, whenever we're beyond the nth term in the sequence. Now we want to show something similar. So we want to show, so it's always good to sort of, before you sort of have a playground, decide what it is that you actually want to show. So we want to show that this is true. We want to show that this is tending to that. So there is an n. So we want to show that whenever we have an epsilon greater than 0, there is an n such that 2xn minus 2x is less than epsilon. So I've just done this, written down this definition, but I want 2xn tending to 2x, so that should be a 2xn and a 2x there. But we can rewrite this a little. We want to relate it. We know that xn is tending to x, so we know something like this is true. So we want to massage this until it looks a bit like that. So what we're going to do, we're going to pull this 2n. So in other words, this is the same as 2 times the absolute value of xn minus x is less than epsilon, i.e. xn minus x is less than epsilon 2. So we want to find a capital N such that this is true. Well, it suffices to show this. But what do we know about epsilon over 2? Epsilon is bigger than 0. But epsilon is bigger than 0, so epsilon over 2 is bigger than 0. And that means that where we've used epsilon here, we could have equally used epsilon over 2. So for every, that's equally as good to use as epsilon, because all we're after is it's a positive number. So every epsilon over 2, there's an n such that it's true with epsilon over 2 there. So sort of got in my head now the idea that I want to write down. So I've now played with this a little, so I can actually write it down. So now I erase all my first work. So this was the important thing. So that we run the argument here. So this is true. We run this backwards now. Okay. So proof. So proof. So we have to start with let epsilon be bigger than 0. So then epsilon over 2 is bigger than 0. So as xn tends to x, there is an n such that for little n bigger than n, xn minus x is less than epsilon over 2. Okay. So we know we're just running this through with that epsilon over 2 is equally valid to use that. Okay. I.e. 2 times xn minus x is less than epsilon, just multiplying through by 2, i.e. 2xn minus x minus 2x is less than epsilon. Okay, so we've got the stuff that we want here to prove exactly what we're. So let epsilon be greater than 0. So there is an n such that for n bigger than big N, you've got 2xn minus 2x. The modulus of it is less than epsilon. So 2xn tends to 2x. So we just did that by converting the definition here into something we knew here. So that was the trick to use in that case. Okay, so now we can run this through again. We just can do this quickly because the second part of the question is almost exactly the same. Be slightly more careful. So the second part of the question just said is replaced that 2 with an a. So a was any real number. Okay. So let's just have a little think. So we want to show. So if epsilon is bigger than 0, then we have an n such that n bigger than big N implies modulus of axn minus ax is less than epsilon. We're going to do exactly the same trick. We're going to pull the a out. Now here we have to be slightly careful because a could be negative or it could be 0, so we just need to pull it out, but it comes out with the modulus signs there, so that's less than 0, which is the same as xn minus x over epsilon is less than the modulus of a. But we can only do that when a is not 0, so this is provided. So we realise there's a slight problem here, provided a is not 0. But that's not a problem, because if a is 0, just look at that case, we just get that if we multiply the whole sequence through by 0, we're just going to get 0, 0, 0, 0, and that's just going to tend to 0, which is 0 times x. So that's fine. So that's not a problem. We just have to consider this one separately, but apart from that, it's fine. So at this point, we can sort of stop and say, right, we just use the same argument as before. So now I run this backwards. So we want to show that that's true, but we know, but if epsilon is bigger than 0, then epsilon over a is also bigger than 0. So we can use the definition of xn tending to x again. Okay, so now we've sort of figured this out. We can write down the proof. Okay, so you might want to go through that again a bit more slowly, but it's the same as the case when a is 2. So let epsilon be greater than 0, and assume a is non-zero, then epsilon over the modulus of a is also greater than 0. So as xn tends to x, there is an n, a big N bigger than, there's a big N such that when n is bigger than big N, modulus of xn minus x is less than epsilon over mod a. Okay, so that's just using the definition, but we've got epsilon over mod a here, which is still a positive number, so we're fine, i.e. mod a times xn minus x is less than epsilon. So, just running out of time, so axn minus ax is less than epsilon. So again, if epsilon is bigger than 0, then there is an n such that when n is bigger than, little n is bigger than big N, that's true. So axn tends to ax. Squeeze that on the end there. Okay.